Hello everyone, I am Kushal Rupesh Pandey from the Academy of Engineering. Today I will be explaining our topic optimization of loss function and best fit line using the gradient descent under the subject exploratory data analytics. Let's start with the basic regression analysis. It's a statistical technique that helps us model the relationship between a dependent variable and one or more independent variables. In simpler words, we try to draw a line called the best fit line that predicts outcomes based on our input data. Regression basically is a foundation for many data science models. It helps us forecast trends, understand variable relationships, and make business decisions. For example, in housing markets, it predicts property prices from location and area based on the current situations. Also, in sales forecasting, it estimates the revenue based on advertising and seasonal factors. This leads to understand the more insight of the production. Now, the linear regression line follows the simple formula that we have been studied in our 10 and 10 plus 2 class. It is y is equal to mx plus c, where m stands for the slope, x stands for the x-intercept, and c stands for the intercept where our line cuts the y-axis. So, basically shows how much y changes for every unit of increase in x. A steep slope means a strong relationship. The point C is where our line cuts the y-axis, the predicted value of y when the x is 0. Our goal is to make this line fit our data as closely as possible by reducing the gap between the actual and the predicted values. Now, measuring the model accuracy. To check how good our line is, we use a loss function, also known as a cost function. It gives a single numeric score to represent how far predictions are from actual result. Lower is always better. The most common one is the mean square error or MSE. It's basically different from our mid-semester examination, which averages, sorry, jokes apart, which averages the square differences between the predicted and actual values. We square the error so that the negative values don't cancel out the positive one and the larger errors are penalized more strongly. This makes the model more sensitive to big mistakes. And here is the given formula for it. Now, the need for optimization. Now, the main challenge, how do we find the base slope and intercept, right? There are infinite possible values for m and c. Our goal is to find the specific pair that minimizes the loss function. This is where optimization comes in. It's like searching for the lowest point in a valley. Other algorithm that help us to find that point is gradient descent. It intelligently navigates the loss landscape to reach the minimum instead of trying every combination. So what the gradient descent algorithm is. Gradient descent is an iterative optimization algorithm that minimizes the loss function step by step. Imagine you are standing on a foggy mountain and want to reach the bottom. Right? You can't see far, but you can feel the slope under your feet, so you take a small step downhill. That's exactly how the gradient descent works. It uses the slope of the loss function to move towards the minimum. The parameters are updated using the calculus and each step depends upon a key factor, the learning rate or the alpha. You can see. So these are the basically the two updated equations for M and C. So the insights from this are: if it's too large, we overshoot the minimum. If it's too small, we take forever to converge, and if it's just right, we reach the optimal point efficiently. Now, more discussing the step-by-step gradient descent process. Here's how the algorithms actually works. There are 6 steps in this process. Here I have classified into 12 steps, but the overview is about 6 steps. They are: first, initialize the parameters. Start with the random values for m and c. Second, compute the prediction. Use the current equation y is equal to mx plus c. Third, calculate the loss. Measure the error using MSE that we have seen earlier. In the fourth step, compute gradients. Find how much the loss changes with MNC. Tell us the direction to move. Then fifth point is update the parameters. Adjust M and C in the opposite directions of the gradient multiplied by the learning rate. 6. Repeat these steps until the loss becomes very small or stops changing significantly. That's when we can say the model has successfully converged. Now let's visualize how this process works. For, so in iteration 0, we start with a random line. It has a high MSE like 245.3. In iteration 5, line adjusting the line start adjusting MSE drops to 142.7. Further over, in iteration 15, it gets closer to the data. MSE is 48.2. In the iteration 50, we reach the best fit MSE of 12.5. As we can see, the loss is continuously decreasing with each iteration, which proves that the gradient descent is effectively optimizing our model. Now, the loss conversion graph. This graph shows how the loss value decreases with the iteration. Initially, the drops sharply because the model is learning fast. Later, it flattens as the line approaches the best possible grade. This pattern is typically for the most well-tuned gradient descent process. Hope you understand these both graphs. Now, we're discussing about the advantages and the limitations of our gradient descent. Advantages are, as stated, it's simple and easy to implement. It works well with continuous and smooth data. It's the foundation of many advanced algorithms, including the deep learning models. It is also a versatile and can optimize a wide range of models. So, as everything has its own limitations, similarly, the limitations are the learning rate must be chosen carefully. Too high or too low can break the process. For complex model, it can get stuck in local minima. It can be computationally heavy for large data set. It needs feature scaling for the better performance. So finally, concluding our topic, we can conclude this whole discussion into main 3 points. First, regression equation. It is been given by y is equal to mx plus c. Also, it defines the relationship between the variables. Second, the loss function or the MSE. It measures how the accurate our model is. Then the gradient descent. Optimize the parameter to the minimum the loss and find the best fit line. Now, understanding the gradient descent is crucial because it's the foundation of almost every machine learning algorithm, from simple linear regression to the deep neural networks. Hope you understand this topic. Now, thank you very much for listening. I hope this helped you understand how optimization, loss functions, and gradient descents work together to build accurate predictive models. This concept truly lies at the heart of modern data science.